Welcome to Lyons Township High School Physics. Today we got an example involving magnetic force on a moving charge, and the charge is going to be moving in the magnetic field such that it's going to make a spiral. Okay, so we have a three-dimensional coordinate system. The I direction, the J direction, and then I cross J is K. So K is actually out of the page at us, but we've kind of drawn it skew so we can see it. And we're going to say there's a magnetic field in this region, and we're going to have that magnetic field point to the right in the I-hat direction. So we'll draw that in. Now, if we launched a particle from the origin in the JK plane, then it would just make a circle. Okay, and we've done problems like that already where you could find the radius of that circle and so on. But we're going to do something a little different. We're going to launch it at a slight angle to the JK plane. We're going to launch it that way initially. So that's going to have an initial velocity v, and by the way, we are going to be using numbers here. And the angle with the J direction will be theta. Okay, and what we're going to find is, well, first of all, what shape is it going to make? Well, assuming it's positive, at this moment it's moving up. If you do our right-hand rule, our Lorentz force rule, we cross that with B, it gets forced into the page. So it's going to make a spiral, and it's going to go basically like this. It's going to do a corkscrew along the I-axis, okay? So some things, and I'll kind of sketch it out, by the way, so it kind of look like this. So we're going to find a couple things about that helix. We're going to find the radius of it. So what's the radius of it? We're going to find, this is called the pitch, which means how far is it from loop to loop. In order to find the pitch, we're going to find the period, how long it takes to make one spiral, okay, one loop. So some data for us here. Let's say that the magnetic field is 2 Tesla. Let's say the velocity V naught is 1 times 10 to the 7th meters per second in that plane, in the IJ plane. Let's say the angle, the initial launch angle is 20 degrees off the J axis. And let's say it's an alpha particle. So an alpha particle is simply a helium nucleus, and the helium nucleus has 2 protons and 2 neutrons in it. So the charge will be plus 2 protons. So Q is 2 protons, which is 3.2 times 10 to the negative 19th coulombs. The mass of a proton and the mass of a neutron are roughly the same. So there's 2 protons, 2 neutrons, 4 particles. And if you take basically the mass of a proton times 4, you get the following: 6.68 times 10 to the negative 27th kilograms. So there's all our data. Now, in order to find the radius and pitch and period, okay, we're going to start by, well, we first need to start by figuring out the components of that velocity. We didn't know how much of that velocity is perpendicular to the magnetic field and how much is along the I-axis parallel to the magnetic field. Well, that's really simple. The perpendicular component, which I'll just name that V perpendicular, that's simply V cosine of that angle. And so you take 1 times 10 to the 7th cosine 20, you get 9.4 times 10 to the 6th meters per second. And then V parallel, and then parallel to the magnetic field is just the opposite leg of that triangle, V sine of the angle. So V parallel is simply V sine of the angle, which is, if you do the math, you get 3.4 or 3.42 times 10 to the 6 meters per second. By the way, that was 9.40. We'll do 3 sig figs, and then we'll chop it down at the end. All right. Now, to find the radius of the circle, okay, well, it's going in a circle, and we're going to use good old Newton's second law. So we know that net force equals ma, okay? The force is Q V perpendicular times B. Okay, and it's a perpendicular component because if the v were parallel to the magnetic field, there would be no force. So the only component of that velocity that we need is a perpendicular component. And that equals ma, and a is v perpendicular squared over r. We're solving this for r. We should have everything else we need. One v perpendicular drops out, and if you solve for r, you get mv perpendicular over qb. Okay? If you plug in chug, so we have our mass, we have our v perpendicular, it's 9.40 times 10 to the 6th. We know our q, that's right here, and we know b, it's 2. If you plug and chug those in, you get the radius of our loop, which is this right here, is 0.0981 meters or 9.81 centimeters. Okay, so the radius of this thing is about just under 10 centimeters. So I've just about drawn it right on the board. All right. There you go. Now, what about the pitch? How far it is from loop to loop. So, for instance, is it a really tight corkscrew where it's doing a lot of loops per centimeter, or is it a really loose one where it's kind of going like that? So what does it look like? Okay. Well, in order to find the pitch, you need to figure out the period. We'll start with v. We know that v perpendicular is 2 pi r over the period. Okay, and we just got an expression for r, and I could plug that number in here, but I'm going to actually plug the expression for it in, because something kind of cool happens when you do this. So we get 2 pi, r is mv perpendicular over qb, okay, and then all over t, okay. So we're setting this equal to that, so some things drop out. So v perpendicular drops out, that becomes 1, okay? And if you solve this for period, so basically you move that over there, you get the following. Period is 2 pi m over qb, okay? Now, something to note about that, it does not depend on the velocity at all. The magnitude nor the direction of the velocity, which is kind of an interesting result, okay? Now, if we plug our numbers into there, we've got m, we've got q, we've got b. So if you plug and chug, you're going to get a period of, and if you want, you can try it out in your calculator, but I got the following number, 6.56 times 10 to the negative 8th seconds. So it's really fast. It goes around once really, really fast, okay? Now for the pitch, well, we're just going to take the parallel velocity times the time it takes to make one loop. V parallel times time. So the pitch is simply V parallel times the period. And we have all those numbers. So if you take V parallel, which we got up there, 3.42 times 10 to the 6th meters per second, times this time, you get about 0.224 meters, which is 22.4 centimeters, okay? So on here, the radius of this guy is about 10, diameter is about 20, and this distance here from pitch, or from loop to loop is also just over 20, which is probably pretty close to right. Yeah, I'd have to make it a little more elongated, but that's actually roughly what this thing looks like. So that's an example of a moving charge through a magnetic field, and it's moving in a way where it creates a spiral. Now, by the way, one common phenomenon that occurs because of this is the northern lights and the southern lights, the aurora borealis and the aurora australis. Basically, charged particles from the sun, they try to enter the Earth's magnetic field at a slight angle, and they spiral into the pole, at which point they actually hit molecules in the air, and that's what causes the glow, the lights that we see. So hope that was helpful, and thank you very much.